Anybody?
Sir, I had a question about pseudo addressing.
Yes.
Sir,
Which address?
pseudo addressing.
Yes, tell me.
Sir, since you are
Oh, you
padding,
had a question. Okay.
yeah,
Yeah.
since you are padding the four MSBs of the uh, program counter, doesn't that limit
Yeah.
us as to how much we can go back uh, by address?
Yes. To a certain extent, yes. But there is a reason why you would like to do that. If you use absolute addresses, uh, like any arbitrary uh, address, okay. Remember, MIPS allow 32-bit addresses, right? So how many bit? So ideally, what do you want? In one instruction, you want to mention the entire 32-bit address.
No.
I mean, you'd like to give the entire address, right? What you are seeing means I have complete freedom of mentioning the entire 32-bit address, so that only 26-bit offset around the program counter limits my ability to jump to different locations. So rather, I'll have the full 32-bit address and I can go anywhere. Is that what you want? I mean, that by common sense, that seems good, right? Is that what you are speaking of?
Oh, yes.
Now, how will you mention 32 bits in one single address? How will you do that? You tell me. Let us go through some options. First point to note is there can be no instruction in which an entire 32-bit address can be bits for code, right? So that option is gone. Second option is have the address broken up into 16-bit registers, 16-bit registers, into 16-bit parts, have them into different registers, combine them by maybe using the LUI instruction and ORI instruction, something like that, to not ORI, maybe have some additional instruction which can copy half part of one register to the MSB side of one register, and the other half part you can use ORI or something like that, loading of absolute value. And then go to that. That is one option. Third option is use the double instruction mechanism to load the constant address into one register, and then go to the address pointed to that register. All these are possible. The question is, if you notice, none of these operations are very simple. All of these operations require some amount of what should I say? Some amount of like a multiple instruction sequence to be executed. Okay, so that becomes problematic. Secondly, if you allow absolute addresses, writing code that will cause memory violation errors will be very, very common, especially say in microcontroller type of situations, which uses microcontrollers are simple microprocessor type devices, which can be programmed from outside, but which performs primarily controller kind of work. It's not very high level general purpose programming, but they are used in industrial applications to perform digital controller types of works. Now these microcontrollers, if you are using, say, the microcontrollers can use many different instruction sets. Okay, some of them have their own instruction set also. Suppose some microcontroller uses the MIPS 32 instruction set. Okay, this microcontroller would probably run without any operating system, which means there is nobody to oversee whether some program is trying to access portions of memory that it should not have accessed. Okay, so you allow 32-bit addresses, you let it jump to anywhere in the program. Okay. Anywhere in the memory, and that might have security implications. Of course, you can stop that type of access by having additional hardware support, which will not allow going to certain portions of the memory. But again, that comes with additional complexity. Another observation is why this still works in spite of taking 4 bits from the program counter is, as was mentioned in the slide, most of the times, the jumps around the program, the branches or jumps around the current location is not by a, most of the times it is 26 bits of offset are sufficient. Okay, not 26 bits, it is actually 28 bits of offset because you have 00 for free at the end. This is sufficient most of the times. Okay, some situations it might not be sufficient, like say procedure calls, etc. But then in that case, we have seen how further using combination of instructions, you can jump to a further location. Even if that is not sufficient, you can jump to one location and then to another location, etc. So all these things the assembler would arrange for you. This type of multiple instructions to perform a jump if one jump cannot manage, one instruction cannot manage a jump because it is so far away. So all these factors combined makes the PC relative addressing mode or pseudo direct addressing mode reasonable. It is very simple to implement. First of all, it is extremely simple to implement. You just collect 4 bits from the MSB side of the program counter and concatenate something with it, and then concatenate 2 zeros with it. So very, very simple. Okay, so that is, there are many aspects to the reason why something else would have been problematic and why this works. Both aspects are there. By the way, there are other instruction sets which might support what you just said. It does not, it can collect, there might be instructions where it collects part of the program counter and then concatenates with it to get the address, but there can also be other instructions where it jumps to a address which is stored in a particular register, an absolute address or something like that. There might be instructions, in spite of all the disadvantages I spoke of, just to have more options of, or more addressing modes, support for more addressing modes, that is possible. Anything else? Okay, students, one important thing I want to mention, and it was mentioned in the email to all of you about the notice of the exam. I would recommend to all of you to please type your answers and convert it to PDF and then submit that file. You can also submit the editable file, like maybe the docx file or the open document file, like if you are using LibreOffice. But I would strongly recommend you doing that. Submitting a soft copy generated from a software like Microsoft Office, and not submits handwritten this handwritten documents and then scan them and combine them in a file. That is going to take time. That is cumbersome. and the size of the file generated can be very large. Especially many of you would probably do it using your phone, smartphones. Nowadays, the camera resolutions are so high that every single page would probably be 4 MB, 5 MB or something. And then combining them into one single file, that will be hugely problematic. Okay. Uh, I would suggest just go just I mean see the questions are such you don't require to draw any fancy diagram or anything fancy. They just require textual answers. Okay, which you can type at a keyboard and convert it to PDF and submit. And there would be some numerical answers that also you can write and submit. And that will be that way it will be easier for our TAs also to grade. Okay.
So in the Moodle for the submission. Hello.
What? Yes, yes.
So during the test, like we will be allowed to submit multiple times, right?
Yes, yes. Yes. You can submit multiple times, yes. It can be said to allow you submission only once, but I think we'll allow multiple submissions. So don't worry about that. But multiple submissions try to avoid because it creates confusion. It is every submission is going to take up 2-3 minutes. Okay. So
Like apart from the time constraint, like
no. What I'm saying is try to avoid it, but multiple submissions will be allowed. Attempts will be allowed.
okay, got it. And sir, I have a doubt in the yesterday's lab assignment that was given to us.
Oh, yesterday's lab I couldn't even join because of the internet outage. Actually, it happened in many areas of the campus. Even CSE department later I had they were having some portions were having problems. Anyways, you tell me what.
So the questions were the first question was to find the GCD of two numbers using the subtraction method.
Okay.
And the third question was to input an integer and check the primality test.
What? Second one I couldn't get.
It was to take an input an integer and check the primality of it.
Yeah, I cannot hear you actually. Maybe it's my network problem, but I cannot hear you.
Hello. Hello, sir. Now am I audible?
Okay, prime number testing. Fine. Okay. Yes. So what is the doubt?
Sir, I had the doubt is that like what will be the range of the input?
You assume a reasonable range and write that as a comment inside your code.
Okay.
Or you in the prompt you write like enter a number within brackets smaller than this, something like that. Enter a positive integer smaller than this.
Got it.
Smaller than 100, say something like that to impose your constraint. If nothing has been mentioned, you can make reasonable assumptions about your. So prime number checking testing. So what is the scheme you are using for prime number testing? This sieve method. I mean the old-fashioned.
So I actually was thinking of choosing the whole complete loop, like instead of skipping the even numbers again and again, like I plus equals to 2.
Yeah.
I was thinking of just using I plus plus, like increasing the I one by one instead of by 2 again.
I'm not fully getting you. So if
Like I was thinking of using a root n algorithm, and
Yeah,
instead
root
of
n sieving is the root n algorithm. Yeah.
and in like in
And you want to use I++.
yes, instead of I plus equals to 2.
But if you, I mean, see, if you are going to test for a prime number, it is usually an odd number, right?
Yeah, I know that. But like
So
using
why do you want to test whether it is divisible by an even number? I mean,
because
what
like
is the logic?
like by using I plus plus, I can reuse that code in the second question as well.
No, that is fine. But why do you unnecessarily want to? If you know that it is not going to give you anything,
Yeah.
Just because you can use it in another problem, why would you write a suboptimal? Why would you perform unnecessary computations? Suppose somebody enters, say somebody enters 23, right?
Yeah.
Say the user enters 23, you want to check whether it is a prime or not. Okay, so you should find it is prime. So why would you check for numbers like 2 and 4, etc.? Well,
Like
I mean,
2
what's the logic?
we have to obviously check for a number. Like we don't know if it is an order.
What?
For 2 we have to check it. Like any input we have to check for 2, right?
I couldn't hear you. Hello.
Yes,
So
sir.
you can also type. You can also type. If you can
Okay.
hear me, you can type. I cannot hear you.
Hello. Sir, am I audible?
Yes, it is better now. I can hear you now.
Yeah. So I was saying like for 2 we have to obviously check for every input that we are getting. And like for further iterations, we move from 3 and then add 2 to our checker. Like
Okay. Okay. Yeah. Okay.
so, like
Yeah, you do whatever you feel makes the code simple and error prone. That will be fine. But you try to explain the logic. I don't know. I have not yet gone through the assignment in detail.
yeah, sure.
Is there an instruction to support instruction to submit some document with what algorithm you followed, a logical reasoning you followed, etc.
No, sir told that write
Like a report or something.
write small comments in the code itself to explain the block, like what
The
the
code itself.
small
Okay,
block.
so in the code itself, you can describe what are your assumptions and why you have adopted that algorithm. Okay. So anything else? See, one thing you will notice later on when you study the MIPS hardware, pipeline hardware, uh, that time. So right now, as you are getting more understanding of the MIPS instruction set, you are developing these questions. Like one student asked at the beginning of the class, what is the advantage of, and why do you use pseudo-direct addressing at all? It seems to be not very optimal. We could have done better. This type of questions are very natural. Later on, when you study the actual hardware, you will find answers to some of this type of queries that you are developing. That why did they did it like this and not something in another way. One of the examples is in the slides. It was discussed that it has BNE and BQ instructions, and it doesn't have branch on smaller than branch on greater than type of instructions. Why? Because the reason also was given, because the hardware design becomes tougher. It might slow down the entire hardware unit, and your entire usable clock frequency will go down. So that's not good. You don't want the entire circuit to suffer just because of one or two bad instructions. Bad in a sense, slow instructions. But BNE and BQ, by their very nature, can be implemented quite fast. On the other hand, we have instructions set on less than, set on all these things. So set on less than is also is kind of a slow instruction, but at least it is faster than the branch instruction, because the branch instruction performs further address calculations, right? So everything together, that first comparison, then an address calculation, and then branching to that address, all these things together in one instruction would have been too much. Rather, they go for a trade-off. They allow a less than comparison, but only reflect the result by setting or resetting one flip-flop or one register. And then you use another instruction to check the content of the register to finally decide whether the comparison has succeeded or the comparison has failed. So this is choice of instructions is very important in a microprocessor. Okay, what to support and what not to support. It's not that they like the engineers did not know how to design the circuit to perform the branch on greater than and branch on less than. They know how to do it. Just that if they support it, the overall hardware would become too complicated and too slow. When we study the pipelining hardware, you will find that, I mean, just as it exists as we are studying, even that is quite complicated. I mean, reasonably complicated. Okay. So further complicating that would be too much, actually. Okay, so there is one question. How are we converting cat to int by masking with 0f? Remember when you were reading in bytes, okay, you are reading in 8 bits at a time. Now, you want to interpret the numbers from 0 to 9. Okay, whatever you have read in, you have to interpret the individual digits by 0 to 9. I mentioned this when I was explaining the program. The number 0 to 9 can be represented using 4 bits. 0000 up to 1001. You do not need more than 4 bits to represent numbers, one digit between 0 and 9. So, if you are reading in 1 byte, okay, what is the significance of the other 4 bits on the MSB side? They have no significance. So I need to kill them off somehow, that is turn them to 0 or mask them off. That's why I mask it with a constant 0x0f. 0x shows it is a hex constant. 0f shows it is the 8-bit constant 00001111. Now, when you perform a bitwise AND of this with your any 1 byte, the MSB 4 bits are killed off, and only the right side 4 bits remain, which are of concern to us. So that these right side 4 bits are now one of the 10 options, 0000 up to 1101. All these 10 options, 1001. These 10 options are there. and because the MSB side etc. have become all zeros, they have kind of become unsigned numbers, unsigned 8-bit numbers. Okay. So this is the reason why we are artificially converting an 8-bit char to a 4-bit integer. Because in this particular case, 4-bit integer is sufficient. This scheme won't work in general. In many other cases, probably it won't work. Just because here we are reading in one digit at a time, okay, where we know that no other character other than a digit would come in, a decimal digit would come in. So this can work like that. And the values are all stored in memory. Okay, the values are not stored as ASCII characters. The values are stored as numbers. If you use the .ASCII command, in that case, they are automatically stored in the ASCII encoding format in memory. I think if I remember correctly, in the example, if you see, those are stored in data format, which means in the way numeric numbers are represented. Okay. Yes, anything else? So there is another request to explain jump addressing. I don't know. So do you mean jump addressing in today's class as we are discussing, or in general jump addressing? What do you want me to explain? So let me just go through the slide. That will be the easiest thing. Just let me go to the slide once more to explain jump addressing. That will be the easiest thing. Okay, so we'll go through branch and jump addressing one more time. Okay. So there are primarily two types of branches in two instructions for branching in MIPS. One is branch on equal and one is branch on not equal, where two register contents are compared. If the register contents are equal in one case, branch is performed, and if another case the register contents are unequal, the branch is performed. Okay, because you need to mention an opcode, you need to mention two 5-bit numbers to represent two registers. You are left with only 16 bits to mention something about this jump location. Okay, now the jump this branch location. When you write assembly language program, the branch location is simply a text level, like we have seen so many times. Say for example, BQ $T2 $0 L2. Just L2 you write and the assembler figures out everything. So how it figures out? It figures out by taking this 16-bit quantity, treating it as a 16-bit 2's complement signed number, multiplying it by 4, that is shifting it 2 positions to the left, okay, and then adding it with the current value of the program counter. Just a moment, student. Okay. So it takes the current content of the PC and multiplies the offset, which is the 16-bit constant, signed constant, and adds. By the way, this microprocessor works, the program counter by this time automatically points to the next instruction that would have executed if the branch had failed. Okay. The microprocessor is designed to operate sequentially, treat every instruction execution as sequential. However, of course, if the branch succeeds, then that sequential execution will probably be broken. But by default, the greedily it assumes that sequential execution will happen, and this assumption creates problems later on, as we will find repeatedly. I have mentioned this. However, this is the way it works. So the assembler sees the current program counter value. It writes the program in the hardware. It takes the program counter current value and adds 4 with it. So adds the offset multiplied by 4 with it. Again, is this optimal? This might not be optimal because only with 16-bit offset you cannot go too far. 16 effectively it is 18 bits, but whatever. 2 power 16, 2 power 15 watts this side or that side. You can 2 power 15 because the MSB, the most significant bit of the 16-bit offset is not used that much. I mean that it basically denotes only the sign. It is not. It does not contribute to the magnitude of the number in any 2's complement or sign magnitude system. One bit you dated just to designate the number, the sign. However, although this is a limited range, most of the times because branches are not very long, typically within 10 to 12 instructions on either side. Very commonly, if it is a loop, maybe within 6 to 7 instructions on either side. These are like not much. 6 to 7 instructions is like 28 words, or even if it is 10 instructions, only 40 words. Whereas we are saying that this mechanism can support up to 50 words. It's a lot. Most of the times this works. Otherwise, it is not. If it is not sufficient, the assembler picks up artificially if it finds that the label L1 corresponds to a location which is far away. so that even with a 16-bit offset sufficient to branch instruction, just manipulates it and breaks it up into two parts. It creates an artificial level L2, where L2 is just the next sequential instruction to the original branch instruction, and it introduces another extra instruction, jump to L1. L1 is that far away instruction. Now the J instruction, as we will see very soon, allows 26-bit offset, and that is 2 power 26 words, 2 power 25 words on either side. No, it allows 2 power 26 words because J is pseudo direct. So it is quite useful. There are two types of pseudo direct jump addressing instructions. One is jump and the other is JAL, jump and link. Jump is the unconditional jump you already have seen. It takes the 4 bits MSB site from the program counter, concatenates with the rest of the stuff. The number it finds that 26 bits, multiplies it by 4, which is to shift by 2 position, just concatenates it. Note that in this case, the 26-bit quantity is treated as no, is this a signed quantity or an unsigned quantity? That's a question. If it is treated as a signed quantity, in that case, no, I think it is not treated. I mean, no arithmetic takes place basically. Just she left shifting by 2 positions. Is the same as adding 2 zeros at the end. So this of the things are evident. Instruction sorry, I think I found. Hello, can you hear me now? Students, can you are you there?
Um, so, good morning, everyone. This is Srikanth. I am your TA. Can you all hear me?
Yes, we can hear you.
Okay. So, the problem is, sir has lost his internet connection and he will not be able to rejoin now. So, the class is ended for today. He also asked me to wish you all the best for the exam, which is coming on Monday at 12. And yeah, I think you can always drop an email to either the TAs or the professor if you have more doubts which you couldn't ask today. Is that fine?
Excuse me, sir. I
Yes.
actually had a doubt about what sir mentioned, that we have to type our answers and not
Okay.
write it. So the numericals, like, it wouldn't be convenient to type it in the document. What do we do about that?
You mean to say that for a question you have done some calculations and the
Yeah.
result is a number and you would not be able to type the number? Is that what
Oh
you're saying?
no, to show the calculation in
I
the.
don't think you're required to show, so
All right.
probably it's fine if you just type in the number.
Okay.
Anything else? Although if you have no more questions, the class is ended for today, so you're free to leave. And if you have any more questions regarding the lab or theory, you can always drop an email.